the organizers for this opportunity to give a talk and to congratulate them for the organization. So today I will talk about moment-angle manifolds. So what is a moment-angle manifold? It's a manifold that you can associate to any simple convex polytope. Simple means that on any vertex, only the minimum number of facets intersect. So, okay. And there are several constructions. I won't insist on the construction of moment-angle manifolds. Many other speakers have done that. Just you can see that you take a polydisk and you take a part of the unit polydisk of Cn, and it is related to combinatorics of the polytope. So you keep a point if it has a few coordinates of modulus less than 1, namely if the corresponding facets intersect in the polytope. So such a manifold is compact, and its dimension is the sum of the dimension of the polytope and the number of facets of the polytope. And it is equivalent with respect to the torus. It's stable by the torus, and this is important because it allows such manifolds to take part of this conference. But today we won't focus on this action. We little discuss of it. To describe a manifold, just mentioning that this is smooth. It has a canonical smoothing. Here is a smooth manifold. And to describe a manifold, an important tool is cohomology. And for a moment-angle manifold, cohomology can be described by topics and polytopes. And for example, we have such a description by Skakov, Bushtabapanov, that the cohomology is given by the Stanley-Reisner ring of the boundary of the dual of the polytope, or it can be also given by the polytope. But what is important for us is that the cohomology can be decomposed into summand, and we have this decomposition. The kth group of cohomology is decomposed as a direct sum over the set of facets, the set of subsets of facets. The set of so it's reduced homology. Of simply the unions of the facets that we consider. We consider the unions of facets, and the homology of this set contributes to homology of the whole manifold, and we have a direct sum like this. Okay. And if we consider only manifolds with prescribed, only subset with prescribed prescribed number of elements. This to prescribe the degree of homology, you prescribe also the okay, you prescribe the degree of homology to which it contributes, and you know this depends only on the number. And a question that is central is, when you give two different polytopes, when do they produce the same moment-angle manifold? So there are several notions of similarity. When you consider a general differential manifold, similarity can concern cohomology, can concern homotopy, can concern topology. The strongest is differential structure when you consider a general differential manifold. And you know there are some notions that are stronger than others. And a question is concerning moment-angle manifolds. Do we have converse implications? And all is unknown in this case, in the case of moment-angle manifolds. Even a question is, if two moment-angle manifolds have the same cohomology, are they diffeomorphic? The question is open. But here, we will consider some notions that are rather stronger than diffeomorphism, because moment-angle manifolds have some other handle with some other structure, and for diffeomorphism, we say that two moment-angle manifolds are diffeomorphic, are diff-equivalent if the moment-angle manifolds are diffeomorphic. So, what are the structures? So, we can consider the toric structure. And the question is, what if we demand diffeomorphism with respect to the toric action? Equivalent diffeomorphism. Is that a strong constraint? And in fact, yes. This is a theorem of Buchstaber, Panov, and Messmann. If two moment-angle manifolds are equivalently diffeomorphic, the polytopes are combinatorially equivalent. Here we only consider combinatorics of polytopes. Two polytopes with the same combinatorics are identified. So this notion is too strong to produce an interesting equivalence, but an interesting problem can be to study if we release the notion of Tn equivalent. For example, we consider equivalence with respect to some subtheory, and well, a particular important is only the diagonal circle in the theory, because the quotient has also interesting properties. But we won't focus on that here. We'll introduce a new notion of similarity, because I recall that we have the decomposition of homology. And we define two polytopes to be graded equivalent if there is a diffeomorphism between their moment-angle manifolds, a diffeomorphism which induces also diffeomorphisms in the bigraded homology. Diffeomorphism between manifolds introduce isomorphism in cohomology, but does such a diffeomorphism always respect the bigrading? We will show that this is not the case in general. So we say that two polytopes are graded equivalent if they are diff-equivalent with a diffeomorphism that respects the bigrading in cohomology. And an obvious fact about this notion of graded equivalence is that the bigraded Betti numbers must be the same. The dimensions of the HPQ, I haven't precised that when you fix here you consider the sum where the number of elements in J is fixed. Sum on Q and of the same, and this one, okay, then you call that P, and this sum is called HPQ. So if the bigrading is respected, the dimension of the spaces are respected. So these dimensions are called the bigraded Betti numbers, and two polytopes, if they are graded equivalents, must have the same bigraded Betti numbers. And we can ask for the converse. Two polytopes with the same bigraded Betti numbers, are they graded equivalent? So this is false, and we have a counterexample that shows that even the cohomology may be different. The dimensions of cohomology spaces are the same, but not the product. Here are two polytopes, and Choi remarked that they have the same bigraded Betti numbers, but not the same cohomology. Their momentum manifolds have not the same cohomology. But there is one case where bigraded Betti numbers are sufficient. An important case for us is the case of connected sums of two-sphere products. So it can seem restricted, but a large class of polytopes give rise to moment-angled manifolds that are connected sum of two-sphere products. It's connected sum of spheres, but of product of spheres, but with two factors in each product. And there I had, well, I don't know if it is necessary, but it's a property that may be automatic, but it is not. It is unknown. Is that each sphere in the products is in some sense homogeneous, that is homology class is in some HPQ. You do not mix different HPQ to get the homology class of the spheres. In the usual cases, this is verified. Usual cases where we are able to prove that we get two-sphere products, but in general, it is unknown. So, now we give some examples of graded equivalent polytopes. I hope non-trivial examples. And the first, historically, even if the notion of graded equivalence was not introduced, is this one. You can take a simple polytope and construct another simple polytope just by cutting a vertex, like on the picture. We have the facet, and when given a polytope, the polytope obtained may depend on the vertex that we cut. This is not the case for the cube because it's homogeneous. In some sense, the automorphic group acts transitively on vertices, but this is false for a generic polytope. And in this case, the graded equivalence class does not depend on the vertex that we cut. If we cut two different vertices, that give rise to two graded equivalent polytopes. And even recently, so when you cut a vertex, in particular, the differential structure of the moment-angle manifolds does not depend on the vertex. And this differential structure has been established recently. And well, this is here is the result. We can remove a ball to the original moment-angle manifold. Take the product with a two-dimensional disk. Take the boundary and take the connected sum with some connected sum of products of spheres, two products of spheres. So we see that this property of having connected sums of two products of sphere appears quite frequently in this theory. Another example of graded equivalent polytopes is the case of neighborly dual polytopes. Okay, neighborly dual polytopes is polytopes that maximize the number of faces when given dimension and number of facets. And a result of Lopez de Medrano and Schittler proved that such polytopes give rise to connected sum of products of two spheres, and then also they only depend on the dimension and number of facets. And it's then easy to prove that we have graded equivalence. A generalization of the notion of vertex cutting is the notion of connected sum. We can see that a vertex cutting is just the connected sum of a polytope with a simplex. And what is connected sum? Just a picture. You can take two polytopes, cut a vertex on each, and then by projective transformation, transform them so that they can be glued to give a new polytope. Okay, they have the same dimension in nature. And here is the connected sum of two cubes. The connected sum of two cubes does not depend on nothing, But generally, we have to choose the vertex that we cut. And we also have to choose how we glue. Here, we can glue, we have a simplex. We can glue a face set here with a face set here, a face set that contains the vertices. And we have the choice here also, which vertex is assembled with which vertex. So, given two polytopes, they may give rise to many different connected sums, but here too, the graded equivalent class is always the same. Another usual transformation of polytopes is it's called flips. Or a flip, we can consider in some sense the smallest variation of a polytope. You move the vertices, the facets, and when a facet touches a vertex that was on other facets, then you move it a little bit further and you have performed a flip. Here you see that the top and bottom facets, okay, are in some sense glued, and the right and behind facets, okay, are separated by the flip. And you see that the edge E disappears and another edge appears. And you can see that E is the intersection of right and behind facet, and the extremal facets of E, facets that meet E but do not contain it, are top and bottom ones. And for E prime, this is the converse. Facets that contain E prime, top and bottom, and facets that meet E prime but do not contain it are right and behind. And the results on graded equivalence is that given a polytope, you can perform flips, and if you consider two simplicial faces that have the same extremal facets, and if you can flip both, then the polytopes you obtain are graded equivalent.
May I ask a question?
Yes.
If I perform the two flips and I look at the dual simplicial complex,
yes,
is that an automorphism on that simplicial complex?
An automorphism? You get two different.
They're completely combinatorially different.
Yes, yes. Yes, the dually it's a bistellar transformation.
But what are the extremal facets?
Yeah, extremal facets are facets that contain, that do not contain, but that contain a facet of it. Here, you consider the top, bottom, facets that intersect on the top of bottom for E. They intersect it at only one extremity. And the constructions on which we will focus here is rather the wedge. So wedge or book for some authors. Here is a picture of what we do. We consider a simple polytope and a facet, and we, in some sense, open it like a book, but you fix the facet. And this gives rise to a polytop which is one-dimensional, where the dimension is increased by 1. And okay, this construction depends on the facet, and here the graded equivalence is not independent of the facet. But what we can remark is that this operation can be iterated. Okay, when you look at the wedge, you can see that its facets correspond to facets of the former polytop. By projections, every facet except the top and bottom correspond naturally to facets of the initial polytop, and the top of bottom corresponds to the facet on which you perform the wedge. And this operation can be iterated. And what is important is that it is in some sense commutative and associative. So the combinatorics of the polytop that you get after iterating the wedging procedure only depends on the number of times you perform the wedge over each facet. So, an important application of wedges to graded equivalence is for graded equivalence of polytops with of dimension d and with d plus 3 facets. Such a polytop, the structure of such polytops is known. Namely, such a polytop is obtained by repeated wedges over well-known polytops. The one is the cube, and the other are called dual cyclic polytops. They are dual of cyclic polytops with 2k with an even dimension and 2k plus 3 facets. The simplest is with k equals 1, you take a two-dimensional polytop with 5 facets, a pentagon. So, if you perform wedges over the pentagon, you get polytops with n equals d plus 3. So the structure of the associated moment angle manifolds is also known. In the case, a little bit trivial, of the cube, if you perform wedges over the cube, you get products of spheres, products of 3 spheres, because the polytop is a product of 3 simplices. In the other cases, we get non-trivial connected sums of products of 2 spheres. And the technical assumption over the class, the homogeneity of the class is satisfied. So here, the graded equivalence of such polytops are only related to their Betti numbers, their bigraded Betti numbers. So, question, can we... So to answer the question, it's important to see what the wedging, how the wedging operations, in some sense, operates on homology of moment-angle manifolds. So just take an example. Here we have considered a pentagon. Okay. In some sense, homology of moment-angle manifolds over the wedge correspond to homology of moment-angle manifolds over the polytope. Consider the wedge over this facet. We take a pentagonal book, and if we consider facet F and facet F prime, their union is just two intervals, which is homotopically equivalent to 2 points. So the reduced homology in dimension 0 has a dimension 1. Here, if you consider the facets in the pentagonal books, the facets that are associated to F and this associated to F prime, there are these three facets, this one, and the one which is under. And there is a homology class that corresponds to this one, but this is a one-dimensional class, of degree 1. Okay. A triangle drawn on this set of facets. And this is what happens when you consider a set of facets that contains F. If you considered a homology class that did not contain F, in some sense it remains the same. It is not affected by this operation of wedging. So when we consider our polytopes, I said that the Betti numbers classified the graded equivalence classes, and the Betti numbers are associated to some sum of the number of times the wedges are produced on each facet. For example, if you consider a pentagon, you can consider the wedging operation performed M1 times on the first facet, M2 times, M3 times on this one, M4, M5. And the moment-angle manifolds has 5. Well, its total Betti rank is 12, but 5 summons in the connected sum. And these are given by I can say M1 plus M3, M2 plus M4. This is not the exact degrees of classes, but these are related. M3 plus M5, M4 plus M1, M5 plus M2. And you have the difference, M2 M2 plus M4 plus M5, etc. And indeed, this one gives rise to odd dimensional degree, and their complements to odd dimensional, to even dimensional degree. Degree is just the dimension of the spheres in the sum, in the products, and in the sum, the decomposition of sphere. Okay, this is written here. The one is odd and the other even. This one corresponds to this. There are a set of two facets that do not intersect, and these others to the complements. So there's three facets, for example. This one, and this one. Yes?
I mean, there are theorems that describe how the stable splitting behaves with respect to this operation. So the stable splitting is geometrically what you look has to follow from that result.
Well, when you perform a wedge, okay, the Qi that are associated to the facets which is kept are gain 1, and the others are the same in some sense.
Yeah, but the draw, we can talk about it after the talk.
Okay. So, in some sense, the Betti numbers are given by these numbers. And, well, we have given these numbers, it's quite, it's very easy to show that we can recover the mi. Okay. And something that I haven't said is that the mi determine uniquely the new polytope. And if two new polytopes are the same, necessarily the mi are the same up to the dihedral group, the group of automorphism of the pentagon. And this is true also with, if not the pentagon, but dual cyclic polytopes, every dual cyclic polytope. So we can recover the polytopes that are graded equivalent in construct like this. For example, here you have to keep globally these numbers, but you can permute them as you want. And for example, if you permute two of these, you can just obtain something like this, where here you remove M2 minus M3 plus M4 minus M5, and here you add it. So you have these transforms on the wedges, and you keep the graded equivalence class. So okay, and after the case n equals d plus 3, we can consider the hexagon. So here we can describe homology with this, and what is interesting is that if you want to consider the graded equivalence, so there are 4 families of transforms like this adding here this S and adding here this S, for families that give graded equivalent polytopes. Here, all these families have 5 parameters, so each time you need a linear relations among the MI. Here you see that the top MI is the mean of its neighbors. Here you see that 2 MI's top and bottom are the same. Here the sums of 2 opposite MI's are equal. Here is A plus B plus lambda and B plus A plus lambda. And here you can see that the alternate sum is 0. Okay, A minus A plus X plus C plus X minus C plus A Y less plus B plus Y minus B is 0. So this is completely described. And the question is that, yes, we have described the, I call it X wedges that are graded equivalent. But questions, is it possible that X wedges are graded equivalent and are not graded equivalent but are diff equivalent? This seems an easy question, but I have not the answer. I have investigated this for some time. It's we can take an easy algorithm, but there are too many cases to control that it seems too long to. But we have some things that are very close to counterexamples. So I will finish by 2 open problems. So I just write that I have these problems of finding diff equivalent but not graded equivalent polytopes. I think I have an idea of how to produce counterexamples. I will finish this talk by 2 open questions about graded equivalent polytopes, giving two conditions, one which may be sufficient to have graded equivalent, one which must be necessary to have graded equivalence. That's questions. The one is about the F vector. Do 2 graded equivalent polytopes have the same F vector? And this question is, I think, also open in the case of bigraded Betti numbers. Do 2 polytopes with the same bigraded Betti numbers have the same F vector, so the same number of faces of each dimension?
But the F vector can be expressed via the bigraded Betti numbers.
Yes.
The F vector is a linear combination.
No, that's correct.
Okay, I didn't know. Okay. So this is not unknown. Excuse me. And in the other sense, perhaps sufficient condition to get graded equivalence is that it's about the skeleton. Okay, a simple polytope is determined by its one-dimensional skeleton, but we can look at its dual, and the dual is simplicial, and to know completely the combinatorics of a simplicial polytope, we need to know the d/2 skeleton. Suppose it's even, and question if we want to know the graded equivalent class, does the d/2 minus 1 skeleton sufficient? This is the conjecture. Okay, thank you. Thank you for you.